Draft system is essential for a power plant system. To enhance the combustion process, large volume of air are required for the fuel to burn. Large volume of gaseous combustion product must also be regularly removed from the boiler furnace. There must be a pressure differential in order to generate the necessary flow of combustion gas or air. The static pressure in the furnace, the various duct and the stack is referred to as draft. Definition of draft: a slight pressure differential between the outside air and the fuel bed furnace that is necessary to keep the air flowing continuously and release gases into the atmosphere through the chimney. Definition for system is a collection of elements functioning as a unit in a mechanism or network, an intricate whole. Now we discuss about the main purpose. First, provide the furnace with the necessary amount of air to burn fuel. A fuel bed is capacity to burn fuel is determined by the volume of air that passes through it per square root of the grid area. Second, to empty the furnace gaseous combustion products into the atmosphere by stacking or venturing them through a chimney.
The boiler draft is broadly classified into two types, natural draft and mechanical draft. Mechanical draft divide into three types, which is forced, induced and balance draft. Natural draft is created by using chimney, where flue gas flow through passage due to the natural pressure gradient. Natural draft can transfer waste gas into atmosphere and used to regulate airflow into combustion chamber. The amount of draft directly depends on the height of the chimney. Mechanical draft is developed to maintain required supply according to the load adjustment, and this type of the draft is used with the irrespective of the atmospheric condition. Forced draft is a type of pressure draft which supply required airflow into the combustion chamber with the help of the external fans. Induced draft is used to supply required airflow with the help of the fan, but this type of draft fan is located near the base of the chimney, which create a partial vacuum in the furnace and flue passage. Those air and flue gases drawn to the boiler due to the comparatively higher pressure of the outside air. Balanced draft is a combination of the forced and induced draft. Balanced draft is the most effective draft, and it is used in a larger boiler. Component of the draft system. A natural draft system relies on the buoyancy of the hot gases to create an upward flow without the need of a mechanical assistant. The main component of a natural draft system includes ambient air. The surrounding ambient air play a crucial role in the natural draft process. As the heated gas rise, they create a low pressure zones, and ambient air is drawn into the system to replace the rising gas. At the boiler, as air or gases are heated, they become lighter and rise, creating a natural upward flow. The chimney is a vertical structure through which hot gases rise due to their lower density compared to the surrounding air. The height and design of the chimney are crucial factors influencing the strength of the natural draft. Forced draft system, induced draft system, and balanced draft system are all types of the mechanical draft system used in a various industry application. Each of the system has specific components that differentiate them in terms of their design and functionality. The difference between three types of draft is a position of the boiler. For forced draft, fan or boiler placed at the inlet of the system. The fan generates positive pressure, forcing air or gas into the system, and opening or duct through which ambient air is drawn into the system by the force generated by the fan. For induced draft, similar to the forced draft system, an induced draft system include a fan or boiler. However, in this case, the fan is placed at the outlet of the system, an opening or duct through which the flue gases or exhaust are drawn out of the system by the negative pressure created by the fans. Lastly, for balanced draft, a fan or boiler is a position at the inlet of the system to force air or gases into the combustion chamber or process. Another fan or boiler is a place at the outlet to create negative pressure, drawing flue gas or exhaust out of the system.
For the case study and the application of the draft system, we will look at the two cases, which is to enhance ventilation, air circulation, and create comfortable indoor environment of a building, and case 2 is implementation of a cooling tower system in an industry. For the natural draft system, we can solve the case 1 by using the passive cooling in building. It relies on the natural process, architectural design, and external environment to maintain comfortable indoor temperature. Generally, it has lower energy consumption as it maximizes the use of natural resources and architectural features. Look at the figure, we can see that the natural wind will bring out the cold air into the interior of the house and drag out the hot air from the river side. For the mechanical draft system, to solve the case 1, we can use the heating ventilation and air conditioner system. It involves the use of heating element, fan, air conditioning unit, and ductwork to control indoor climate. This system has an air holding system to send the cold air to a room, and the hot air will return back to the air holding system to cool out. By this air circulation, the room temperature can be maintained, and compared to the natural draft, this system needs high install cost and energy consumption, but it has an advantage is it can provide the precise control over the indoor temperature, humidity, and air quality. Besides that, it also can function in a larger space. For the case 2, the industry cooling tower can be separated by two categories. One is natural draft system and one is mechanical draft system. For the natural draft system, it operates based on the buoyancy of hot air, it allowing it to rise and exit to the top of the cooling tower and creating a natural airflow. It is more environmental friendly because it lower energy consumption as it relies on natural convection and does not require electrical power for fan. And one of the disadvantages of the natural draft system is it typically larger and require a tall structure due to the need for a chimney effect for effective natural convection. For the mechanical draft system, this cooling tower utilizes the mechanical fan or blower to force or induce air through the cooling tower. The airflow is controlled and enhanced by the mechanical system. This type of cooling tower needs higher install cost and energy consumption, but it is easier to install in locations with space constraint and can be more compact and adaptable to various site conditions. Compared to the natural draft system, it has higher performance, so that for the industry with a larger scale, nobody need a mechanical draft cooling tower to fulfill the requirement.
So next, I will briefly give out the equations related to natural draft. And first here we have the draft or pressure difference, and here are the related variables for the equation. And in the case that we assume both air and gas are ideal gases, we can assume that pressure of air is equal to pressure gas. The universal gas constant of air is equal to the gas, and then we also need to find the temperatures, and more on that is we need the gas temperature at the inlet of the chimney and the exit of the chimney. Now next we have the actual draft or the actual pressure difference equation, as you can see highlighted here, and also the effective stack or chimney height, which is equal to height of the stack plus the height of the plume gas. Now for natural draft, there are three equations how to calculate the plume rise or the plume height. First is by the correlation by Carson and Moses, which is often used, and then we have the correlation of Briggs, and as the stability class is based on the have to be referred to the table. And here is the Fol-Holland's formula for calculating the plume rise, and what needs to be noted carefully here is the pressure, atmospheric pressure, is in the unit of millibar. It cannot be in other unit, it must be in millibar. So now we have the example question over here, which requires us to calculate the height of the plume using the correlation of Carson and Moses. By using this equation, we first have to identify all of these variables, and now we have to collect all the information from the question. Here we have is the temperature of the gases, temperature of the air, the diameter, and the height of the stack. Also we have is the velocity of the wind. All we need to do is convert it, very easy. And then we also have the mass flow rate of the gas at exit. Now, using the equations for the mass flow rate and density dry air, which is P equals to pressure over RT, and here we are going to use the temperature of the gases because we are going to find the velocity of the gases at exit, which is Vs. And then using the mass provided and the density that you have calculated and the area, which is pi over 4 diameter square. And here we have the velocity of the wind, the velocity of the gases are 84.09 meter per second. Now, using all that we have found, we will put it into the equation, and here we have it, the answer. But here the answer, we see we get 1842 meter, which is 1.8 kilometer high of gas plume, which seems rather unrealistic. So we will have to reevaluate our calculations and see what we did. Now, from the equation of one source, it is stated that the Q heat emission we simply use joule per second, but in other sources they divide the answer in kilojoules per second. Here are the sources, the online sources that I have referred. Hence, we try out recalculating it using those equations, giving the Q in kilojoules instead of joules, which is too big. And then here we have a more appropriate answer for the plume height, which is 57.58 meters high, rather than the 1.8 kilometer high gas plume. So now the answer looks more logical, and we would accept this kind of answer.
Another example of calculation for mechanical draft, the question is a textile factory has a battery of 6 Lancashire boilers, each supplying 6 tons per hour of steam at 16 bar and 250 degrees C from feed water at 30 degrees C. The boilers burn fuel oil of calorified value of 40,960 kJ per kilogram with an overall efficiency of 75%. For efficient combustion, 60 kg of air per kilogram fuel is required, for which a draft of 20 mm of water gauge is required at the base of the chimney. The flue gases leave the boilers at 320 degrees C. The average temperature of the gases in the stack may be taken to be 300 degrees C. The atmosphere is at 30 degrees C, assuming the velocity of gases at stack at Z to be negligible. Determine the height of the stack and the diameter at its base. So, to answer this equation, we need to derive the information given, which is mass flow rate 6 ton per hour or 6,000 kilogram per hour. Pressure is equals to 1.1013 bar or equals to 1.1013 times 1000 kilopascal. Gas constant Ra, which is 0.287 kilojoule per kilogram dot K. Atmosphere temperature Ta equals to 30 degrees C. Average gas temperature Tg equals to 300 degrees C. Overall efficiency, which is 0.075. Height of the draft H equals to 20 mm. So the first step to solve this question is to write the relation for draft produced to calculate the height of the stack. So we know that the draft pressure difference formula, which is draft equals to GH times PA rho A minus rho G. And then by the draft system, we can get H times G times rho W equals to GH PA over RA times 1 over Ta minus 1 over Tg. By substituting the value, we can get the height, which is equals to 36.44 meter. And the next step to obtain the enthalpy at inlet from steam table, which is P1 equals to 60 bar and T1 equals to 250 degrees C. Thus, by referring table, we can get H1 equals to 2919.2 kilojoule per kilogram. For the next step is to write the relation for efficiency of the boiler. So we know that efficiency of boiler equals to ms times H1 of minus H feed water over mf times CV, and we need to times with 6 since we have 6 boiler. By substituting the value, thus we can get the mf equals to 0.847 kilogram per second. And the next step is to calculate the mass flow rate of air by using the following relation: air fuel ratio equals to 16. MA equals to MF equals to 16, and thus we can get mass air equals to 13.552 kilogram per second. So next step is to calculate the total mass flow rate of the mixture by using formula MFG equals to MA plus MF. Thus we can get MFG equals to 14.399 kilogram per second. And the last step that we need to solve the equation is to calculate the diameter by using following relation. MFG equals to rho FG times AVG, and thus by substituting the value, thus we can get the D equals to 1.073 meter. In conclusion, the draft or draft system is critical element in power plant combustion system, playing a key role in optimizing performance and environmental impact. Basically, there are two types of draft system, which is natural draft and mechanical draft. The draft or draft system consists of various components such as air preheaters, fans, damper, and control system, and many others. By understanding its component and function, power plant operator can implement strategy to enhance the efficiency and reliability of their combustion processes. Thank you very much from our group. Happy to watching.